Okay, welcome back. And now we're going to take a look at a couple of specific alternating terms, and then we're going to do a proof for the alternating harmonic series. Okay, so these two series here are just a couple of examples of alternating series. The first one you can see is a geometric series where the absolute value of r is less than 1. So this is a convergent series, a geometric series. The other one here is what we call the alternating harmonic series. Now, the harmonic series, as we know, is a divergent series, but it turns out that the alternating harmonic series is a convergent series. So we're going to show the proof of that, and then this proof can be generalized to show the convergence of general alternating series. And I'll explain that a little later. But to show that this is going to be a convergent series, we're going to take the odd terms, or the odd partial sums, and the even partial sums, and show that both of those sequences converge. Okay? And then by showing that those two sequences converge, and then showing that by taking once we show that the odd term partial sums, the odd term partial sums, and the even term partial sums converge, then we can show that by putting those together, they both must converge and converge to the same number. And we'll also show you what that number is. Okay, so let's start by looking at the odd terms. Okay, so we're going to the odd partial sums. Okay, so we'll consider 2k plus 1. Okay, for all k less than or equal to 0. Now, since since 1 over 2k plus 1 is less than 2k. Okay, so what we're doing is we're taking all the odd terms, odd partial sums, the terms of the odd partial sums, right? So since this is true, then we can write keep messing up here. So we're going to take this is equal to this partial sum plus, getting ahead of myself, minus, well, this minus 1 over 2k, right? And then plus 1 over 2k plus 1. So that's this partial sum. So I'm taking this partial sum, subtracting off 1 over 2k plus 1 over 2k plus 1, and that's going to be less than s of 2k minus 1. Okay, so that's true because here I have this partial sum. So I have this partial sum here. This is equal to this partial sum here. And I'm subtracting off this one, but adding something smaller. So I'm subtracting something slightly bigger. So if you add these two together, you're going to get something that's negative. So you're subtracting, to get to this, you're subtracting something from this, so it's going to be less. Okay, so this is going to be something that's ultimately a negative value. Okay, so this is going to be less than this. Okay. Now, that means that this is a decreasing series. Now, also, let's pair some terms up. So if we write out the terms, so let's write out some of these terms. S of 2k plus 1. So obviously it's going to start with 1/2. Minus 1/3, or excuse me, I'm sorry, keep forgetting 1. 0, this starts at 0. So this is going to be 1, right? And it's going to be minus 1/2, and then it's going to be plus 1/3, right? So plus 1/3, minus 1/4, plus 1/5, minus 1/6, and then plus, and it keeps going on, and we get okay. And then it stops here at 1/2k plus 1. Okay? So if we write out these terms for the 2k plus 1, well, notice that if we group these like so, this is greater than 0. Right? Because if you have this is positive, this is positive, this is positive, so you can see that all of this is going to be greater than 0. It's a decreasing function that's bounded from below now. Okay? So that's where we're going to have. So let's I don't want to write this. Okay, so the sequence is bounded below, right? And then since the sequence of partial sums is decreasing, and bounded below, then we know by the monotone convergence theorem that the sequence is convergent. And now what we do is we're going to show, similarly, we're going to show that the sequence of even terms, s sub 2k, is an increasing function that's bounded above. Why? Well, let's look at the partial series, right? So if we look at the partial sequences rather of 2k, well, we know we can write something similar because we can start with 2k minus 2, right? So this is equal to s of 2k minus 2 plus s of 2k minus 1, oops. That's not what I want to write. 1 over. So this is 1 over 2k minus 1 minus 1 over 2k and this is greater than that partial sum. Now, how is that? Well, here, now this is positive and this is negative. So the difference between these two, because this one is slightly bigger than this one, now we got positive terms, so this is going to now be an increasing sequence of partial sums. Okay, so now this is an increasing, right? And since we can also write this, okay, let's do s sub 2k equals 1. Okay, so we're going to repeat what I have at the top, 1 minus a half plus a third minus a fourth. Where do I want to stop? I want to make sure okay, good. Plus a fifth. Okay? So I'm going to do plus, plus, and then let's do this, minus, minus 2, minus 1, okay, so let's look at this here, partial sums. Now what I want to do is I'm going to change, just so we can see this, I'm going to change these to plus negatives. So I'm going to change this to a plus negative 1/2, plus negative 1/4, and I'm going to change this to a plus negative 1/2k minus 2. Okay, and what I'm going to do is I'm going to group these a little bit differently than what I did up here, and I'm going to group these two, and then I'm going to group these two, and then I'm going to group these two all the way down. Okay? And so now what happens when I do that? Well, here I got 1, and this turns out to be a negative number, right? Because I'm adding something smaller to a negative number that's bigger. So this is bigger negative, right? A half is bigger than a third, right? And since this is negative, this whole group here is going to be negative. So this is negative, and so I'm taking 1 and I'm subtracting off something negative, right? But that negative number is getting smaller, okay? All the way to here, okay? So what I can say is this is an increasing, right? This is increasing, but I definitely have something that's less than 1. So I can say that this whole thing is less than 1 because I'm adding on something that's negative. So I'm actually subtracting. So this is positive, right? And the rest of the terms is negative, but that difference between the terms, these groups, is getting smaller and smaller and smaller. So I'm subtracting off a smaller and smaller piece, but nonetheless, I'm taking the fact that this is an increasing function, an increasing sequence of partial sums, and the partial sums I know is less than 1. Okay, so again, by the monotone convergence theorem, right? So therefore, by the monotone convergence theorem, the sequence of S of 2k is convergent. Okay, now, since we can rewrite s of 2k plus 1 as s of 2k plus 1 over 2k plus 1, and we know that the sequence of these partial sums and the sequence of these partial sums is convergent, and this we know is going to 0, right? We can take the limits of these. Oops. Okay, so now, letting the limit of this equal s, right, since this converges, right? So this converges to s, and the limit as k approaches infinity of s of 2k, plus now the limit of this is going to 0. So by combining that, we can say, we show that the limit of the partial sums of s sub 2k also converges to s. So they converge to the same value of s. So since the odd terms and the even terms in the sequence of partial sums converge to the same limit s, it can be shown that the sequence of partial sums converges to s. Okay? And therefore the alternating harmonic series converges to s. Okay? So let me say that one more time. Since the odd terms and the even terms in the sequence of partial sums converges to the same limit s, it can be shown that the sequence of partial sums of the sequence of the alternating harmonic series also converges to s. Okay? Now, it can also be shown that s is equal to the natural log of 2. Okay? And that's it. Have a great day.